Hello and welcome everybody. In this video tutorial, we are going to preview vectors. We'll preview what they are, what they stand for, how we can represent them, and how we can work with them mathematically. Let's begin. Please remember to pause or rewind this video as necessary. Most of the quantities in physics are vectors. This makes proficiency in vectors extremely important. Vectors are quantities that have both magnitude and direction. So let's talk about what these are. Magnitude represents the size or amount of a vector. It's the number part. Direction is the alignment or orientation of any position with respect to another position. In other words, which way it points. Which way the vector points is represented by the direction. If a quantity does not have direction, it is referred to as a scalar quantity. A scalar quantity has magnitude only. These are quantities that have no direction. Some examples include time, mass, temperature, distance, speed, energy, and voltage. Voltage is really related to electrical energy, so those would definitely be connected. A vector is a quantity that is going to have both magnitude and direction. It's a directional quantity. Some examples include velocity, acceleration, force, displacement, momentum, and torque. Now, in terms of vector notation, it's represented by an arrow that points a certain way and a letter with the standing for some variable with a half arrow on top. The length of the arrow is proportional to the vector's magnitude. The direction, well, that's which way it points. Now, negative vectors are just simply having the exact same length as the vector, but they point in the opposite way. When we add vectors, especially in a straight line, but when we add vectors overall, the result of adding vectors is called the resultant vector. And for now, the resultant vector is going to be denoted with a generic capital R for resultant. Now, if two vectors are being added in a straight line, it is as simple as arithmetic addition, meaning if vector A had a magnitude of 3 units and vector B had a magnitude of 2 units, that means vector R is going to be having a magnitude of 5 units, which is, of course, 3 plus 2, because those two vectors are pointing the same way. Now, if you subtract vectors, remember, subtracting is really just adding a negative. So that would be very similar to, let's say, 3 units pointing to the right, negative 2 units going to the left, and 3 plus a negative 2 would be 1 unit going to the right. But what if you wanted to, let's say, add or subtract vectors that are not pointing in a straight line? Maybe one vector points one way and another vector points in another direction. Well, we have two means of doing so. One method, the first method we're going to look at, is called parallelogram method. And here's how it works. I'm going to animate it for you so you can see how it works. And then we'll take a look. The result is pointed out here over on the side, okay? And we're going to see how we get those results. In parallelogram method, what we do is we take the two vectors, okay? So here's vector A, tracing it out. I'm going to pull vector A just kind of over here to the side, I guess. And I'm going to do the same thing with B, like that. And notice I'm putting both tails together, just like that. The next thing I do is I complete the other half of the parallelogram. Like that. Move that here. Move that here. The resultant vector is a straight line from start to finish. And you can see that represented right here. Now, what if we're subtracting vectors? Same idea. So we have vector A. I'll slide vector A on over here, but I'm going to put it over here this time. And we're going to put, with the tail of vector A, a negative b. So a minus b is a plus a negative b. So we're going to, if b goes to the right, negative b would go to the left. And we're going to put those two tails together just like that. Again, completing the parallelogram. Just like that. And the resultant vector is a straight line from where the two tails meet to the opposite end. It's a good idea and a good practice to get in the habit of just sort of highlighting the resultant vector so that it pops, or putting it in a completely different color. And you can see both of these solutions represented over here on the side. So parallelogram method is one way we're going to look at what is called vector geometry, which means how do we essentially add two vectors to see what the result of those two vectors would look like. Now, another method we can use, one more thing to point out. Parallelogram method is only valid for adding or subtracting two vectors. If you're going to add or subtract more than two vectors, you need to have another way. Well, that other way is called tip-to-tail method. Okay, and the way it works is we take the tip of the second vector and we place it at the tail of the first one. So I'm again going to copy A. Okay, I'm going to slide it up here this time. Okay, and then I'm going to copy B. And I'm going to slide that up here. Notice I'm placing the tail of B right at the tip of A. To finish off this, we simply draw a straight line from where the whole vectors begin, from the very beginning to the very end. That is our resultant vector. You can see that represented right here. And if you pay attention to it, you'll notice that A and B are exactly the same as the A and B over here. They're identical. And notice vector R points exactly the same way it did when we used parallelogram method. So tip to tail, same idea. We're going to take A, okay, I'll do this kind of over here where I have room. And at the tip of A, I'm going to put negative B. Just like that. So again, tip to tail. The tail of the second vector goes at the tip of the first. And the resultant vector is a straight line from start to finish. You can see that represented clearly right here, and it is consistent with the other method. It is readily apparent that both methods arrive at the exact same solution, since either method is essentially a parallelogram. It is useful to understand both systems. In some problems, one method is advantageous, while in other problems, the alternative method is superior. Part 8. Draw the resultant vector using parallelogram method of vector addition. Let's take a look at letter A. Okay, I am going to complete the parallelogram. There we go. Slide that on over. Slide that on over. And the resultant vector is a straight line from start to finish. And I'm going to go ahead and highlight that just because. At this point, take a moment to pause the video. Try your best to complete B, C, D, and E using parallelogram method. Okay, check with the solutions below and see if it compares to what you have. Notice, in each of the cases, B, C, D, and E, we complete the rest of the parallelogram and draw a straight line arrow from where the two tails meet to the opposite side. Part 9. Draw the resultant vector using tip-to-tail method of vector addition. Label the resultant vector as R. Okay, we can see a couple examples have been done for us. already. At the tip of A, we put the tail of B, just like this, the resultant vector, straight line from start to finish. And in this example, we put the tip, or the tail, excuse me, of negative B, so flip that around, we get negative B, at the tip of A, and the resultant vector looks like this. Let's take a look at a couple of these. X plus y. So in vector x plus y, we're going to copy vector x. We're going to copy vector y. Okay, I'm going to slightly just move them on over a little bit. So at the tip of vector x, we're going to put the tail of vector y. And the resultant vector is a straight line from start to finish. T minus s would be t plus a negative s. So let's copy t. Now negative s would point up and to the right instead of down and to the left. Move these out into the space here. Just like that. Resultant vector, straight line arrow from start to finish. Please take a moment and pause the video. Try letters C, D, E, and F yourself. Then check with my solutions when the video resumes. Now note, E and F have 3 vectors. Not to worry, it's just simply tip to tail, tip to tail, tip to tail. In other words, 3 times instead of 2 times. Okay, taking a look at my solutions, you can see that we're going to put the, for letter C, we're going to put the tail of, make it a little more clear here, the tail of V right at the tip of V of P. The resultant vector is a straight line from start to finish up and to the right. For letter D, we're going to put the tail of negative D at the tip of C. Again, resultant vector is pointing down and to the right, straight line from start to finish. And then if we add vectors A, B, and C, straight line from start to finish puts the resultant vector slightly down and to the left. Finally, A plus a negative B plus a negative C puts the resultant vector very steeply up and to the right. Yes, it is passing through the negative B vector, but that's fine. Still works fine. Now we're going to talk about how we can reference the vectors in terms of the parts of the vectors that point in a certain direction. So what does a positive or negative direction mean? How is it referenced? The answer is coordinate axis system. In physics, a coordinate axis system is used to give a problem a reference frame. You're going to hear me state things like set up a positive reference frame or a negative reference frame. Now, the truth of it is reference frames can be established however you want. If you want going to the left direction to be a positive reference frame, that's fine. That means to the right is negative. If you want going down to be positive, that's fine. That means going up has to be negative. However, I think what makes most sense to me is to keep it consistent to what you've learned in your math class with regards to how the number line typically works. Positive x values go to the right, positive y values go up, negative x values go to the left, negative y values go down. And so let's try and keep the exact same reference frame with regards to how we will work it. Now, what happens when you are essentially specifying a vector that's not in the x or y direction, right? Well, then you're going to have a vector pointed at some angle, okay? And there's 4 possibilities. You can either be up and to the left, like you see here. You can be somewhere in this quadrant, up and to the right, down, somewhere down into the right, and somewhere down and to the left. Okay, now with those 4 possibilities, you're going to be referencing the vector with an angle. One thing to note, positive angles are counterclockwise from 0 or the positive x-axis. Negative angles are clockwise from that same origin point. You can see if vector r points up and to the right, what we will do is we will reference that by saying The x direction of r points to the right, and the y direction of r points up. In part 10 here, we are going to draw the vector components from each of the following vectors. So you can see vector r is pointing up and to the right, up to the left, excuse me. In part B, it's vector r is pointing up and to the right. In vector C, r is pointing down and to the right. And in vector D, it's pointing down and to the left. So let's go ahead and take a look at these one at a time. In letter A, we would draw vector components, and typically it helps to draw them with a dashed line. This would be negative r in the x direction and positive r in the y direction. Letter B, if r is pointing up and to the right, we have positive r in the x direction, and we also have positive r in the y direction. Letter C is down and to the right, so we're going to go positive r in the x direction, but we're going to go negative r in the y direction. Finally, in letter D, r is pointing down and to the left, so we're going to have negative r in the x direction and negative r in the y direction. In this next section, we're going to take a look at how trigonometry and vectors are linked. Well, you might recall that using trigonometry, r is going to be the magnitude of the vector, but it's also the hypotenuse of a right triangle. And so that's exactly what we're doing, is we're using a little bit of right triangle trigonometry. Now, you'll notice that the cosine is going to be adjacent. I'm going to write this as the adjacent side. And I'm going to write this as the opposite side. And it's the adjacent side, Rx, over the hypotenuse, R. Sine would be the opposite side, Ry, over the hypotenuse, R. And you can see that represented in these two equations here. In both cases, we would simply multiply both sides by R. And you have your equation right here. The adjacent side of a triangle is always going to be r cosine theta. The opposite side of the triangle is always going to be r sine theta. In part 11 here, we're going to practice finding and calculating vector components. Now, in each case, you are given r, the resultant vector, and theta, which way it points. Okay, let's take a look at one of these. So r sub x would be r cosine theta, or 89, cosine 150 degrees. And then r sub y is going to be the same magnitude, 89, but this time times the sine of 150 degrees. Rx would be about negative 77. Ry would be about 44 and a half. At this point, go ahead and pause the video, and let's try B, C, D, E, F, and G yourself. When the video resumes, you will be able to check and compare your answers to mine. Okay, please take a moment to compare your results, check your work, make sure you're doing it correctly. And let's move on to part 12. Now, in part 11, you were taking a look at having a vector magnitude pointing in a certain direction, and you were resolving it into its horizontal and vertical components. In part 12, you're going to go exactly in the opposite direction. In other words, you're going to be given the horizontal and vertical components, and you're going to use Pythagorean theorem to figure out the vector magnitude, and you'll use an arctangent formula to figure out the direction in which way it points. So let me kind of slow that down a second and show you where it's all coming from. So if you have a vector that's pointing, let's say, vector r, it's pointing at some angle theta like this, you know you have a component that's horizontal, we'll call that Rx, and you'll have another vertical component, we'll call that Ry. And since this is a right triangle, we know we can use, right, Pythagorean theorem. A squared plus b squared equals c squared. But if you look carefully, a squared is nothing more than Rx squared, right? B squared is nothing more than Ry squared, and c squared is just r squared. So if you square root both sides, right, you can see that's what we get right here. And we're going to be using the Pythagorean theorem to figure out the magnitude of the resultant vector, otherwise known as the length of the hypotenuse. Now, if we take the tangent of the angle, which is opposite over hypotenuse, the tangent of the angle would be Ry over Rx, right? Opposite over hypotenuse. Okay, now take the arctan of both sides, and you can see we're getting this arctangent formula right here. So those are going to be the two equations we're going to end up using in order to find the vector magnitude and the direction. Okay, let's go ahead and take a look at part A. So in part A, r would be the square root of Rx squared plus Ry squared. Plug into that, and we're going to go 600 squared plus 400 squared. Okay, and we're going to get approximately 721. Okay, you might want to pause the video for a second and try putting that in the calculator yourself and prove that you can do this. Okay, to get direction, we're going to take the arctangent of the y component, 400, over the x component, 600, which is essentially the arctangent of 4 over 6, because it'll all reduce down, which is essentially the arctangent of 2/3, which is the arctangent of 0.67. So when we do that, we get an angle of approximately 34 degrees. Now, pay attention to the sign of these components here. Since both of them are positive, you know that your vector is pointing up and to the right in quadrant 1. So if this is your axes, you know the vector's pointing off in that direction right there, which means 34 degrees, right, would be that angle right there. Since it's a positive angle, it's 34 degrees from positive x-axis. It's helpful to include the reference from where the angle's coming from. Okay, let's take a look at letter B. In letter B, r is equal to, and we're going to go negative 0.75 squared plus negative 1.25 squared. Pause the video, take a second to put that in your calculator. Okay, we should have gotten about 1.46 when we put that in our calculator. Okay, taking the arctangent of this, we're taking the arctan of negative 1.25 over negative 0.75. Now, interestingly enough, because the negatives cancel, we get a positive angle of 59 degrees. But be careful, think about where that's coming from. Both of these are negative components, meaning it's going to be pointing in quadrant 3 down here, which means that 59 degrees is really coming from the negative x-axis. So 59 degrees from the negative x-axis is one way to state it, or you can add it to 180 degrees, which would be about 239. So about 239 degrees from the positive x-axis. Both directions are equally valid, so as long as you give a reference to where the angle's coming from, you can still use the 59 degrees, but you can't just say 59 degrees by itself. Okay, we're giving an exact reference from where that angle is coming from. Okay, at the moment, go ahead and pause the video and attempt questions C, D, E, and F, and we'll compare results in just a moment. Checking your results, we can see that in letter C, the magnitude of the resultant vector is about 36. And when we calculate theta using the arctan formula, we get negative 27. What's important to note is that if you draw a small sketch of where the angle is, you'll see that it's 27 degrees coming from the negative x-axis. Remember, clockwise angles go negative, counterclockwise angles are positive. So it's 27 degrees from the negative x-axis. Or you could say subtract 27 from 180, and it's 153 degrees from the positive x-axis. Letter C, we can see the magnitude of the vector is about 0.011. When we calculate the arctangent formula, we get an angle of negative 54. Drawing a small sketch, that puts this in quadrant number 4 down here. So negative 54 degrees from the positive x-axis, or subtract from 360, and it's 306 degrees from also the positive x-axis. In letter E, the resultant vector magnitude is about 24,413 using Pythagorean theorem, and it's a quadrant number 1 vector. Therefore, the 35 degrees you get is only coming from the positive x-axis like you see here. And finally, letter F, 325 squared plus 99 squared, square root that using Pythagorean theorem, and we get about 340 for the magnitude of the resultant vector. The arctangent of those components gives us about 17 degrees, also quadrant number 1, from the positive x-axis. Okay, so up until now, we've completely examined the geometry and the sketching of vectors. We've examined the mathematics behind vectors, which is just simply right triangle trigonometry to find the vector components, or Pythagorean theorem and right triangle trigonometry again to find the magnitude of the resultant vector and its direction. So now let's take a look at how vectors are actually used in physics. Well, they're used everywhere. Speed, let's first of all differentiate between speed and velocity. Speed is a scalar quantity. That means it has magnitude only. So when you see a number that says 10 meters per second, it means the object is going 10 meters every second, but the 10 is the magnitude. That's the speed. You're not told which way the direction of the motion is going. Therefore, it is just speed. Velocity, on the other hand, is a vector quantity. It has both magnitude and direction. Think of speed as the numerical part of velocity. So if you saw a velocity that said 10 meters per second north, 10 meters per second is the magnitude, right? And the positive x direction is the direction, okay? Or north is the direction, okay? Now, there are different types of speeds and different types of velocities, okay? So there is instantaneous speed. That would be the speed or velocity at an instant in time, right? If you look down at your speedometer and it says 20 meters per second, you're traveling 20 meters per second at that moment, right? The speed will obviously change as you take your foot off the gas or apply more, acceleration. Average speed or velocity is when you take a trip and you basically speed up and slow down at various points, and then you get sort of an average for the whole thing. And that's done by taking the total length that you traveled divided by the total time you traveled. Okay, and then constant speed, if you have the cruise control set the whole time at one constant speed, right, then you're not changing. So here's a question. Will an object traveling at a constant speed of 10 meters per second also have constant velocity? Well, not always, okay? If the object is curving then you are changing direction, which means the velocity is changing, which means you are accelerating, okay? So you have to be going in a straight line at a constant speed in order to be going constant velocity as well. If you're curving, no. Okay, so rate, speed, and velocity are rates. A rate is a way of quantifying anything that takes place during a time interval, and we'll see that pop up. Okay, rates are easily recognized. They always have time in the denominator. We're going to see various rates pop up this year. So anything per unit time is considered a rate. So taking a look at our very first physics equation, we have V equals x over t. And I'm actually going to put, so we have a couple of one. I'm going to put delta x. Delta x actually stands for displacement. And we're going to write in V equals d over t. So V could also stand for speed as well when it's paired with d, which stands for distance. So distance is just the scalar length of something. Displacement, on the other hand, is the change in position. Okay, so let's take a look at how this would apply. Okay, letter A. A car travels 35 kilometers west and 75 kilometers east. What distance did it travel? Well, I think what's probably best to do is keep our reference frame consistent with what you've learned in math class up until now. In other words, let's have positive directions going to the right and going up. We'll have negative directions going left and going down. That means on a map, that would of course be east, north, south, and west as well. Okay, keep that in mind. So if we're going 35 kilometers west, let's draw an arrow going to the left, 35 kilometers. Okay, and then it's going 75 east, so it's going a little more than twice that to the east. Okay, what distance did it travel? Well, just add them up. 35 plus 75 gives you, let me see, what, 110? 110 kilometers. Part B, car travels 35 kilometers west, so I'm going to copy the exact same picture, and 75 kilometers east. This time, what is the displacement? Well, the displacement, I'm going to zoom in on the picture, is really just a straight line from start to finish, meaning the blue arrow that you see right there. That's going to be the displacement. And you can see it's pointing to the right. Now, how do we actually calculate it? Well, you're going to add up your individual displacements. In other words, negative 35 kilometers because it's going west, plus 75 kilometers because it's going east, right? And adding a negative, of course, means you're subtracting, and you'll get 40 kilometers. But you have to now, since it's displacement, it's a vector, you have to give it a direction. So 40 kilometers going east. And you can see that's representative of the blue arrow there, which is about a little bit more than half and pointing to the right, which would be east. Okay, car travels 35 kilometers west and 90 kilometers north. So there's 35 and there's 90. Total distance, again, just add them up. 35 kilometers plus 90 kilometers would be 125 kilometers. Okay, but now if we take that exact same scenario and we want to find the displacement, remember the displacement is a change in position, meaning a straight line from start to finish. And in 2 dimensions, well, that's the hypotenuse of a right triangle now, isn't it? So we're going to go delta x is going to be the square root of 35 squared plus 90. Whoops, excuse me. Plus 90 squared. Okay, and we put that in our calculator, 35 squared plus 90 squared, and then we square root that number, and we get about 97 kilometers. But it's displacement, so you need a direction. Well, think about what we did in the vector practice, the vector preview practice earlier. We need to take the arctangent of that. So the arctangent of 90 over 35, so 90 divided by 35, then go ahead and take the arctan of that, and you get about 69 degrees. But look at what's coming from. 69 degrees coming from the negative x direction, okay, or north of west. So 69 degrees north of west. What that means is 69 degrees above west, pointing to the north. The way we wrote that earlier was 69 degrees above the negative x-axis. Remember, the negative x-axis is west on a map. Okay, now we get into some actual speed problems. So, first thing we do is annotate the question, okay? The bicyclist pedals at 10 meters per second. There's our speed. In 20 seconds, there's our time. And we're looking for distance. Make a list of your variables, okay? D is question mark. Speed is 10. T is 20. Okay, the equation we use is V equals D over T. Okay, that's our speed equation. We're going to multiply both sides by T in order to get distance by itself. And distance is speed times time. Okay, and we're going to go 10 meters per second times 20 seconds. You should be able to see how the units of seconds drop out, and we're left with a unit of meters, which is the appropriate unit for distance. And 10 times 20 would be 200 meters is the distance the bicyclist pedaled. Okay, letter F. We have 250 kilometers, that is a distance. 300 meters per second, that's a speed. How long does it take? We're looking for time. But the units of distance are not consistent. So what we're going to do is we're going to change this into meters. So distance in this one is actually not 250 kilometers, but 250,000 meters. Speed is 300 meters per second, and time is what you're looking for. Okay, so speed is equal to distance over time. In order to solve for time, we're going to go ahead and do what's called the switcheroo, in which case time and speed switch places, and it's time equals distance over speed, or 250,000 meters divided by 300 meters per second. And we get about 833 seconds. Okay, now that's one possible answer. If you divide that by 60, that would be about 13.9 or almost 14 minutes. It's fine to leave it in seconds, though. Okay, skydiver falls 3 kilometers in 15 seconds. How fast are they going? So 3 kilometers is distance, 15 seconds is time, and we're looking for speed. So distance would be 3,000 meters. We're changing the units. Time is 15 seconds, and we're looking for speed, distance over time, and we can just plug right in. We don't need to rearrange the equation. And we get about 200 meters per second. Okay, Now we're going to take a look at the difference between average speed and average velocity in 2 dimensions. So let me go back to those calculations we did up here, okay? I'm going to copy part C. Car travels 35 kilometers west, 90 kilometers north. What is the average speed? Well, average speed is going to be distance over time. So the total distance from that, if you recall, was 125 kilometers. Just look at your answer for part C right here. So 125 kilometers over 2 hours. Divide those two. And we get about 62.5 kilometers per hour. We'll just go ahead and leave it in kilometers per hour. It's fine. Our normal unit of speed would be meters per second, but for the purpose of this exercise, we'll just leave it. And then in part I, we're looking for average velocity. Well, velocity goes with displacement. So I'm going to use our answer for part D. Copying and pasting our picture in there. Okay, average velocity would be displacement divided by time. Going back to part D, we can see our displacement was 97 kilometers. In other words, the hypotenuse of that triangle there. So 97 kilometers divided by the same 2 hours would be about 48.5 kilometers per hour. So sometimes average speed and velocity are the same. Okay, sometimes they're not. It does depend on whether you're going 1 dimension, meaning in a straight line, or 2 dimensions, meaning your path changes or curves. I hope you found this video tutorial helpful. Please come and see me if you still need help.